Hello, I'm going to teach you today about Snell's law and index of refraction. First, let's start with the concept of index of refraction. As light goes from one material into another, it bends. So it'll have different angles it makes with the normal when it hits the surface. Though, if you've got something light that hits a surface at 90 degrees, it won't get bent at all. But yeah, if it does hit a surface, it's going from, say, like air with an index of 1, basically, into water with an index of 1.33. It's going to bend towards the normal in this case, if it's going from the air into the water. If it's going from water into the air, it'll bend the other way. But first, let's talk about what the heck is this index of refraction. Now, your standard formula is this guy. This is the way it'll show up on your formula sheet. This is saying, hey, your index of refraction, which is just kind of a measure of how slow light travels through the stuff. So this is just like, how slow does light travel through it? That's equal to the velocity of light in a vacuum, which is in your data pages, because it's always the same in vacuum. If I can spell vacuum right. Anyway, velocity of light in vacuum is always 3 times 10 to the 8, 300 million meters per second. So that's just a constant, and then you divide it by the velocity of light in the stuff. So if we're talking water, we're talking about the velocity of light in water. If we're talking air, we're talking velocity of light in air. Stuff. So if you think about it, if you rearrange it, this is what you divide the speed of light by in a vacuum. I think it makes more sense like this. Like it gives you a better idea of what index actually is. It's just this number you divide the speed of light in a vacuum by to end up with the speed of light in the stuff. So anyway, you can rearrange this. You either know the index and want to find the velocity of light in the stuff, or you know the velocity of the light in the stuff and you want to find the index. So you always know the speed of light in a vacuum. It's just a constant. So these are the two ways you'd use this formula. Like an example here, want to know the speed of light for the following mediums. For water, you'd just be like, hey, my velocity in water is equal to 3 times 10 to the 8. That's C. So it's equal to C over N. And N is 1.33. And that would equal speed of light in water. And then you can do the same thing for diamond and plexiglass. Here we've got the other version. If we know the velocity of light in the stuff, we can find the index of it by just taking our speed of light in a vacuum and then dividing it by the speed of light in the stuff. 2.1 times 10 to the 8. This one's easier. 3 divided by 1.5 is 2, so this would have an index for 2. For B, A, I'm not quite sure offhand. But yeah, throw it in the calculator, you're done. 3 over 2.1, done. Anyway, so that's index of refraction and this funny little formula. The other thing you gotta, well, two other things you might need to use. One thing to note, like as light goes from like one substance into another substance, you can look at it as like a ray, like a laser light, like a beam, or you can look at it as kind of a wave. They're both just different ways of like looking at it to make it make sense to you. So this would be kind of the same idea. This is the same beam being refracted by just looking at it as wavefronts. One thing you should definitely know, and is likely going to come up on a test, is velocity is determined by the medium. for always, like tension in a guitar string, and it's like how thick the guitar string is. That determines it. The temperature of the air and its density, that determines the velocity. So velocity of a wave, any wave, is determined by the medium, the junk it's passing through. The medium. And again, this medium is just a fancy word saying the stuff it's passing through. Like if this is air, the medium is air. If this is water, the medium is water. Medium could be a certain guitar string, could be air in this room, whatever. So for any wave. So this might come up, make sure you know it. Also notice, like, if you've got this refraction going on, like it's the same source. So you're not changing the frequency here. So as light passes from one medium to another medium, it's still the same color. It's still the same frequency. Like you got the same number of crests, you've just slowed them down. You've reduced the speed and you've reduced the wavelength, but the frequency has stayed the same. And that works for other waves. Like if you've got some light source and it goes from some substance into another substance, then the frequency's got to stay the same. Otherwise, you need to like make more crests. Like that's not happening. You're just slowing them down, so they're bunching up. You're changing the wavelength and changing the velocity. So frequency stays the same as it passes from one substance to another. C stays the same. It's just the wavelength that changes. As wave moves from one medium to the other. So velocity changes, that changes. You've got Snell's law, or why don't we go for the other one? First formula is kind of the ratio of things. Velocity of the wave in substance 1 divided by velocity of the wave in substance 2 is equal to the wavelength in substance 1 divided by the wavelength in substance 2, which kind of makes sense because velocity equals wavelength times frequency. And if you have wavelength times frequency over wavelength times frequency and your frequencies are the same, they would just cancel out and it's wavelength over wavelength. So how fast it's moving in substance 1 divided by how fast it's moving in substance 2 equals the wavelength in substance 1 divided by the wavelength in substance 2. If you think about it, n is just equal to c over v. So this is just a constant that would cancel if you did n1 over n2. It would be c over v1 divided by c over v2, and do a little kissing and flipping, and that would equal to v2 over v1. So notice this is just the flipped version of velocity. So I'm going to throw that in here as n2 over n1. And Snell's law is sine of the angle just goes with the velocity. Sine theta 1 over sine theta 2. And if you're going to use this formula, just pick any two. Like, say I want to relate index to wavelength in the different stuff. I'd just use these two. I'd use that as a formula. Pick any two fractions and make them equal to each other and then solve for what you're looking for. That's the gist with that. And the other one is Snell's law, which is just basically like making these equal to each other and just rearranging. So index in substance 1 times sine of the angle in substance 1 equals index in substance 2 times sine of the angle in substance 2. And this is the angle relative to the normal. Notice we always measure relative to the normal, imaginary line perpendicular to the surface. The interface between the mediums. Anyway, example of how to do this stuff we got. So why don't we do a visual example? Something like this. So we start off in the first substance at an angle of 45 and an index of that, and we end up with an angle of 65. By the way, since this is bigger, I know my index has got to be smaller. They're kind of inverses of each other. So as angle gets bigger, the index has to get smaller because they kind of multiply to each other. Really, this times sine of this equals this times sine of that. But if one goes up, the other has to go down, and sine theta goes up as theta goes up. Anyway, so you can just do n1 sine theta 1 equals n2 sine theta 2. And so it would just be like 1.5 is the index we start in. Sine 45 equals the index we're looking for times sine 65. So if we wanted to solve for this guy, we'd just do 1.5 sine 45 divided by sine 65, and that will equal what we're looking for. So this one's not too bad. Gets a little trickier sometimes when you want to solve for like theta, depending on how good you are with inverse sine. See if we can find an example. Okay, so angle of incidence of light traveling through air strikes water is 30 degrees. So we just got kind of light coming in at 30 degrees. It's in air. And it's going into water. This one requires you to know that water has an index of 1.33. So in this case, it's just 1.5 sine 30 divided by, or why don't we do the whole thing? So n1 sine theta 1 equals n2 sine theta 2. If we want theta 2, why don't we solve for sine theta 2? So it would just be like sine theta 2 equals 1.5 sine 30 over 1.33 if we divide both sides by 1.33. And then to get rid of the sine, we just got to do inverse sine to both sides, arc sine. So then it's just theta 2 equals 1.5 sine 30 over 1.33, but inverse sine. So just don't forget how to do an inverse sine. Try a couple like that. You should be good. Yeah, I'm not going to give you anything too terrible. Just know the gist of these ones. Any sneaky ones? I mean, this one's a little sneaky. You just convert this to meters, convert this to seconds, divide it to get velocity, and once you know the velocity in the material, you got the speed of light in the material, and then just do speed of c divided by v. So you do like distance over time using correct units equals v, and then c over v equals n once you found v. All right, hopefully that makes this more clear. Good luck.